So for this
Professor,
submittal,
the
yes,
criteria says that our bolt size should be 3 by 4.
which load criteria? 3/4 of an inch?
Yes, sir.
Okay. Go ahead, please, and use 7/8 of an inch, if you don't mind.
Okay.
So I'm going to put this here. Two common size bolts that we usually use in construction is going to be 3/4 and 7/8 of an inch in structural steel. So it depends on the designer. I mean, so I want everybody just to have the same hand. So you make it easier on me for grading, you know? So you're going to come up with number of bolts. This is going to be your item number 1. Now, what's item number 2? You need to check shear on the beam web. Now, when you check here the shear on the beam web, you need to consider the holes. Don't forget you're going to have here holes, right? When you cut the section through here. You do the area of the web, you need to consider the holes, right? 3 holes. You have the size of the bolt, and therefore you can figure out the size of the hole, and then you can do a check on the shear. So you check shear on the beam web. Item number 3, you can say check the shear tab thickness. And once you do this, I mean, in order for you to do this, you need to come up with the thickness and then check on the shear, and of course you need to account for the holes. You're going to have holes here for the bolts. And then item number 4, check the weld between the shear tab and the faceplate. Now, when you do the bolt check, you're going to have eccentricity in the bolt, because you understand that the force is going to be coming down here, like in this direction, as an action, which is SF sub U, the reaction that you calculate out, and the reaction is going to be right here. So when you do the bolt check, you need to consider eccentricity. Where do you have this? Sure. It's going to be this table here, eccentricity on the bolt. When you do the weld, you have also eccentricity, because here's applied load and here's the reaction. When you do the bolt, you can say here's applied load and here's the reaction. So be sure when you consider the bolt or the weld that you need to consider also the eccentricity. The weld is going to be based on this table, and the bolt is going to be based on this table. So both of these two items need to be checked: the bolt with eccentricity and the weld with eccentricity.
Sorry, in the bolts, isn't the eccentricity 0? Because the
No,
FU is going through them.
this is true. You have a force coming through here. How about the weld? You have also a
Already
force
we
going
have
through it.
3-inch eccentricity.
Same thing for the bolt. See this? You said let's not use the eccentricity on the bolt and use eccentricity on the weld, correct? That's what you're saying.
No, sir, I'm saying that there is 0 eccentricity on the bolts because FU is going through them.
Okay. How about the weld? Is there any eccentricity on the weld?
Yes, there is. It's 3 inches over here.
How do you know that? Because this is going to be the applied force and this is going to be the resistance.
Yes, sir.
But if I come here and cover this with my hand and they said, well, let's say that you don't see it, you're going to say the force is going through the weld. Okay, so I'm going to say, why don't we do this?
I have no idea.
So I'm gonna do it like this for you. Where's the force coming from? Let's say coming from here. Transfers to the bolt. Is there any eccentricity?
Yes, sir. Now
3
there
inches.
is.
So okay, so actually you have eccentricity in both the weld and what? And the bolt.
Bolts.
Bolt, yeah. So we have eccentricity in both of them. All right. So I'm
Yes,
gonna
sir.
say here number of bolts. Consider the eccentricity. Do not forget this, please.
Okay.
And also when you do the shear or the weld check, you need also to consider the eccentricity. Please don't forget these items. Otherwise, you're gonna be losing points for it. You don't want this.
Okay, sir.
Now, is this an important thing that you really need to submit and you need to work on? I'm gonna say yes, definitely, because this is gonna be in your second midterm. It's gonna be very similar to it, something very similar to it. So the advice here, be sure that you check all of these items and you do it and you know exactly how you are doing it and put it in kind of like algorithm or steps. So when you are taking here your midterm, you can run through it. You don't want to spend time just thinking about it. Where should I start? Where did I put my notes? And also, please be sure that your notes are handy and available to you. I hear from some people that they have trouble to find their notes and to download all of these files. You know, the presentation files, that they have trouble to download it. You shouldn't be downloading it during an exam. You should have everything downloaded to your computer and just go ahead and use it. I would rather maybe print it, print the small version, the one that has 2 slides, just print it and keep it next to me. It's gonna be much easier if I want to go through it than having it on one computer, whether I have one screen or 2 screens. I would understand the struggle that you're going to be going through them when you're working on one problem here. So, all right. Other item that I want to show you, and I want you also to start on it, is going to be the submittal number 3 for the project. Already posted. It's going to be due the following Sunday, but this is not a small one. This one, I'm sure that you're going to come up with questions. So be sure that you work on this coming weekend or this week. I mean, I'm not saying keep the stuff for the weekend, but what I'm saying is be sure that you address it, you study it this weekend. So on Monday, you can ask me questions, or Tuesday in the office hour.
Sir, is this submittal also included in the second midterm?
You see the date?
Yes, sir.
Okay, this is after the midterm.
Okay.
Okay, all right, thank you. So it says here, determine the size specific seismic parameters SS and S1. I guess you guys, we discussed how to do this. And then you find out SD1 and SDS and SD1, consider site class D. There's 2 site classes. One is called site class D and the other one is called site class D default. Please use just site class D. So be sure that you do it like this. Site class D, not the default. Also, I want you to figure out the size design category. You're gonna see it there in the code. We need the load criteria. As we said, when it comes to seismic weight, you're gonna include here what? Weight of the concrete deck and steel deck, steel beams, additional dead load, partition weight, 10 PSF, exterior skin. We discussed this in details. How do you figure this out? And then if you have permanent equipments like the AC units and the rooftop, as we say, is going to be maybe 10 kips. Is this what you say, 10 kips? I mean, am I correct about this 10 kips?
Yes, sir. It was 10
Okay,
kips.
so I want everybody to consider the same number. I don't want to see lots of changes between your answers. So you need to come up with this seismic load criteria. You're going to be writing it in details. At the end, you're going to say, here is the weight per square foot for each level. So it's going to be like a small table. You know, I'm expecting a small table like this at the end for conclusions, right? So we're going to say, okay, what do we have here? You're gonna have here, let's say, roof, stuff like this. Roof, third, second, seismic weight per square foot. 1, 2, 3, and then after that, the floor area. So you can come up here and then put the floor area. 1, 2, 3, and then after that, total weight, which is a seismic weight, total seismic weight. You just fill in this spaces, right? This is what we'd like to get to, if we can.
Sir, you said we have to do it roof, floor, and
This is here. Just give you the roof, right? Just give you right here in this one. And then here we're gonna have the third level, third floor, and this is gonna be here the second. So actually, the third floor and second floor they're gonna be identical. Just gonna be a copy here. Roof is gonna be different. As we said, roof doesn't include any concrete. Third and the second will include some concrete, right? This is here, item number 4 says, determine the design seismic weight of each level. So you're gonna have it here in the last column. You're gonna have the seismic weight. You're gonna be taking this uniform load multiplied by the floor area or the roof area is gonna give you total seismic weight for each level. After that, we need to figure out the design seismic base shear. We don't know how to do it yet. I'm gonna be going through it today and also for next time. And then after that, I need the story force. So also we need the same tables. So at least for this weekend, if you are able to do this, this is gonna be great, right? Everything here above, this is gonna be great. You don't wanna squeeze yourself after the exam or even during the exam. Do you guys recall the R factor that we said for dual system? Did we call this to be dual system, I guess? Right? What's the dual system? Anyone recall the dual system? No. In our case here, if you guys recall, we have mount frames and then we have brace frames. So we have actually dual system. This is what we have discussed. These are the equations that you're going to be using to figure out the seismic coefficient CS and then multiply by the total weight. So actually when it comes here to this equation, I'm going to take you back here. This is going to be here the dual system in the Y direction. And this here dual system, the X and Y direction. And this actually matches our case for our project. It's going to be all dual system. Now we said that we're going to be using the static method, and the static method means what? Means this method here. It's going to be called the static method. The static method, your total base shear is going to be the total seismic forces active on the building. It's going to be equal to the coefficient that you're going to be working on multiplied by the total weight of the building. Meaning, in your project here, in this table, you're going to do here the weight. You see here, this is going to be here W. So in this column, you're going to put here the weight. And then at the bottom, you're going to do here total weight. It's going to be all the way at the bottom. Total weight, and then we're going to say W for the entire building. This weight here is going to be the one that using this equation, total weight of the structure. And here are some directions or some guides here. How would you find out the total weight of the building? Now, after this, you're going to be coming here to these equations. I guess we said SDS. We understand that you're going to be figuring out based on the map or based on the location according to the address I gave you. This is going to be for SDS, SD1, and also is going to be T sub L we say we consider to be 12 seconds. And then after that, you're going to be doing these two equations. This is going to be the CS that you need to use. It has a maximum and a minimum values that you need to consider. Also, we discussed this risk categories. We said that we're going to be in this seismic risk category 2, meaning that this importance factor, I sub E, is going to be equal to 1. This is going to be ours, right? We're going to be using IE or equal to 1. And for the natural period, for now, in your determination for the forces, for the seismic forces, we're going to be using this equation. We just say this equation, excuse me. We're going to say here that natural period used in our analysis, right? We quote approximate natural period is going to be equal to C sub T times Hn to the X. The story height in our case is 14 feet times 3. So Hn is going to be equal to 14 times 3. Your X component, you can go ahead and use it 0.8. For C sub T, I'm just going to be using here 0.028. Okay? I understand that this is a dual system, but dual system cannot really be taken under this all other structure systems. It doesn't make any sense. And I guess I explained the reason of this. Very soon after we are done with this submittal that you're going to be working on, submittal number 3, we need to work on determination of natural period using accurate methods. And this is going to be the equation that you can use when you have single degree freedom system. But when you have multi-degree freedom system, you're going to be using this equation. And I'm going to be showing you an example to which we are going to be doing it exactly this method here. Once we find out here the accurate or exact natural period, it's going to be the accurate method, natural period exact if you like, you're going to compare it to C sub U times TA. So here, T max, the actual one, is going to be equal to C sub U multiplied by TA. This is going to be your maximum value. You're going to compare it with T from dynamic analysis. We call this, you can still call this dynamic analysis if you want to. You do some dynamic analysis to figure out natural period for multi-degree freedom system. C sub U is going to be based on the SD1 that you're going to be figuring out. You remember here, I have SDS and SD1. So based on SD1, you can determine here your coefficient C sub U. Here's a simple graph that I developed for this reason. This graph is not in the code, just a simple graph. But what you see here in the code is going to be this table. It shows here C sub U on the y-axis and SD1 on the x-axis. So if your SD1, which is going to be most likely is going to be more than 0.3, you're going to be in this region. And in this case, your C sub U is going to be equal to 1.4. If SD1 is going to be, let's say, in this area here, less than 0.1, your C sub U is going to be 1.7. If it's going to be in the middle, you can do interpolation. So interpolation here is going to be allowed between these two values, 1.7, 1.4, and this is going to be the equation that you can use in there. Now, the R factor that we're talking about, which an indicator of the ductility of the structure system that you picked. It says here it's going to be based on the structure system for the building type. We have this bearing wall systems. So this bearing wall systems is going to be very similar to this. I don't know if I have a picture here for it. No, I didn't put it because it doesn't happen in structural steel buildings. So bearing wall systems, this is where you're going to see here maybe reinforced concrete shear walls, masonry shear wall, and you don't really have a kind of a moment frame or a brace frame. In this case, we call it here bearing wall system. Let's give you the R factor. Let's give you the overtrans factor. This is going to be a very important factor. And this number here is going to be the amplification factor. This when you want to check the drift, we're going to be checking it with this factor here. I'm going to show you later on how this is going to get done. For the seismic design category, based on each seismic design category, we're going to figure out the building height limit. So for example, if you are planning to use a special reinforced concrete shear wall, you can use it. Let's say that you have seismic design category of D, like what we usually have here in California. It's going to be, so you have a limit here for the building height is going to be 160 feet. It's going to be the limit. NL means no limit. NP means not permitted. You cannot really use it. So this system, we call this A1, this is going to be A2. So A2 system cannot be used in seismic design category D, excuse me. So it's really important that you need to figure out the size design category to know the limits of your building, whether it's going to be allowed or not allowed. So here's the first category, bearing wall system, and you have all the types. And let's say that you're doing here very simple building, like masonry, for example. So you can go here to special force concrete masonry walls, and the R factor is going to be equal to 5. Simplification factor is going to be 3.5. So I said, okay. How about if I'm doing a small house? I'm going to say small house is going to be this light frame wood. It's going to be A15. It's going to be part of this category. It's going to be A15. Your R factor is 6.5. And deflection amplification factor is going to be 4. The overall tolerance is going to be 3. And you cannot use it in size design category D. Your limit is going to be 65 feet only. So once you get to 65 feet, you cannot go beyond this. This is going to be your limit for the seismic. How about this building frame system? You can see this building frame system, these are the buildings that we're looking at, and it does not include moment frame. It doesn't have bearing wall. So now we don't have any bearing walls, right? So again, going back here to our pictures for the plans. I'm gonna say, in here, I have this building frame system. In a building frame system, you have columns, you have framing, right? And then you have either brace frame concentric or eccentric. It's gonna be made out of steel in this case. So I'm gonna jump here to it. I'm gonna go here to the building frame system category. Yeah, look at the first one. It says here, steel eccentric brace. You remember the eccentric brace? This is where you have the link beam. And your R factor is gonna be 8. It has a limit of 160 in size design category D. So as you see here, usually I look at size design category D. And most of the building we do is giving this size design category. If you have a special concentric brace frame, right? This is going to be special concentric, not eccentric. So eccentric, when you have the link beam. Concentric, when there is no link at all. You see what happens to R factor? Drop down to 6. Now, if you are doing here some analysis for your building, and you have two options here to choose from, option 1 and option 2. We call this B1 and it's going to be B2. And you have the same weight for the building. Which one do you think is going to be resulting in higher seismic forces? Is it going to be B1 or B2?
B2.
B2 is going to be higher forces. And how would you compare it to the B1, like percentage wise? Any answers? 25%? Okay, yeah, makes sense. Yes, absolutely. So are these questions here critical that I'm asking, the conceptual? You say absolutely. And this is actually what you're going to see in your midterm. Now in your midterm, I'm not going to give you your analysis for seismic, right? It's going to be too lengthy and I don't have time, and also you did not do your submittal. So I cannot ask you like analysis or analytical questions about this chapter here. But what I can do, I can ask you lots of conceptual questions, right? You remember the moment frame, you remember the plastic hinge, dissipation of the energy, right? The R factor, which one's going to be more ductile? If you use this or use that, so be sure that you understand all of these factors and then you do kind of quick comparison. So for example, I'm going to say, which system is more ductile? Is it the steel eccentric brace or the steel special concentric brace?
Eccentric brace with R.
Eccentric is ductility high, right? So when this R factor is high, it means ductility factor is high, because R here, response multiplication factor, is a representative of the ductility factor. Another question, which one's going to be resulted in, your choice is going to be resulted in a higher force? We're going to say the one with a smaller R. It's going to be the type of questions I may ask. How about the limit? You think I can ask you about the limit? I'm proposing here to build wood construction. Of course, I'm not going to say wood construction. I'm going to keep it to steel. So I'm going to say here in this steel. I'm going to say, what is the height limit if I have size design category? I'm going to say maybe E, and I'd like to use steel ordinary concentric brace frame. You're going to say it's going to be 35 feet, right? This is going to be the type of question I'm going to be asking in this midterm about the seismic. And then you have ordinary, and then you have a special. If you look at this, it says here special, and then ordinary, and then you have another structure steel. Steel and concrete composite ordinary brace frame, this is new systems, and it's taken 3. Steel composite plate shear wall, we're not going to be doing it. So I care more about the brace frame, concentric, eccentric, and the moment frame. So, okay, now I understand where the arcs can be coming from. And if you like to indicate a system, the easiest way that you call it, let's say B1, B.1, B.2. This is going to be the easiest way, just to make it easy for people to know. And instead of writing the whole thing here, right, you can just call it B1 system. So we know B is going to be the building frame, A is the bearing wall, and C is the moment frame system. So we can say in moment frame system, I have a special, it has an R factor of 8, which is the same as eccentric. It's very good, right? So when you combine them together, you still have an R factor of 8. I don't see it here, but I don't think I'm going to be taking this 8 plus 8 divided by 2 doesn't work this way, right? No, there's a different way of doing it. And again, the overstrength is here, and your C sub D is going to be here, and look for this any seismic design category. You don't have any limit, which means that you still can be using still a special moment frame for, let's say, 50 story. It should be fine. Look for this intermediate moment frame. No limit, no limit. And then all of a sudden now you come here to 35 feet, and then not permitted, not permitted. This one you make it intermediate moment frame, and then you have ordinary moment frame. So actually the special moment frame, just a quick thing here so that you guys know, the special moment frame is going to be the one that's going to have this reduced beam section, the RBS, or the one's going to have the cover plate. I'm going to take you back here quick and say, what are you talking about? I'm going to say this one here. When you have this cover plate, or you have an RBS, we call this RBS, reduced beam section, right? This when we cut a piece of the flange. So if you have an RBS, or you have this top flange, you can call it the special moment frame. So once you put them there, if you're not going to put them there, look what's going to happen to you and to your analysis. Let me jump to it. So if you use the RBS, your R factor of 8 for cover plate. If you don't use them, you can go to intermediate or maybe even the ordinary, and your R factor drop. Even if you just take him out, look what happened. The amount of seismic force is going to get doubled on you. It's not good. Or look at the 3.5 compared to 8. I mean, they're going to say, no, let me just say use a special moment frame. So I guess this here is going to give you an idea. If I say a special moment frame, and instead of I say a special moment frame, I'm going to say a moment frame with an RBS. Now someone's going to say, what is the RBS? We didn't cover it. I'm going to say, no, it's covered. It's right here. Here's the RBS. This is called here RBS, reduced beam section. Sometimes also you call the duck bone, because it looks like a duck bone, you know, if you have this cut from each side. So this gives you the RBS, right? So once you have the RBS, this is going to qualify you to have a special moment frame. What is a special moment frame? You can go here to moment frame system, right? And you can use R of 8. Okay. Now, if you have a dual system like the one we were talking about, your R factor is going to be equal to 8 or 7. Now, let's see here what's going on. It says here, we need to read this because this is going to be very critical, and it's going to be also a critical question for us. It says a dual system with, okay, so here's the definition of the dual system. A special moment frame. So you need to have a special moment frame. If you're going to be doing a dual system, it has to be a special moment frame. So the question can come like this. Can you have a dual system with ordinary moment frame or intermediate moment frame? I'm going to say no. It is not in the code. You cannot do it. The code says only it's going to be special moment frame. With what? I'm going to say with. Now, I know that there's something here, 25%, but I'm going to say with steel eccentric brace frame. So yes, you can do it. It's going to be a factor of 8. So you do a eccentric brace frame, it's going to be a factor of 8. If you do it with a special concentric, it's going to be 7. So it's going to reduce a little bit, right? Your response mitigation factor, the R factor, ductility. Ductility is going to drop down. So if you do a dual system here, and you bring a special moment frame, you add it to concentric brace frame, your R factor would drop down to 7. So if I'd like here to propose two systems and then ask you which one is more ductile, is it the special moon frame just as a moon frame system? Like in here, I'm going to call it here C1, C.1 system, or D2, which means a special moon frame with concentric brace frame. So what you need to do is to look at this system at C1, you're going to be looking at this 8, and then compare it with the R factors. It's going to be D2, it's going to be 7, and you say this one is going to be ductile than this. It's going to be the answer. And you see here, it has no limit. It's going to be the beautiful thing. So if you have size design category D, you'd like to go to a high-rise building, you can use here a dual system easily. And in this case, maybe you'd like to use 8, factor of 8. Okay, good, great. Now let me read the rest of this definition. It says here, a special moon frame capable of resisting at least 25% of the prescribed seismic forces. What does mean capable of resisting 25%? Which means you're gonna do here your analysis. Here is your analysis, right? You're gonna put here the moon frame. Here's the force. Can I take you to go to one of these buildings? This is gonna be a very good example that we can do our marking on. Can I put the seismic forces here? Here the total seismic force, I'm gonna call it here V. Now what is resisting this seismic force? I'm gonna say this moment frame, this eccentric brace frame, and this eccentric brace frame, and this moment frame. Now which one has higher stiffness? Is it gonna be the brace frame or the moment frame? Brace frame. Now I want you here, please, to stay focused because the number one, this is gonna be in your midterm. Number two, you need it to work on your project. So when you run the analysis here, let's say that you build a model, a 3D model, and you put the moment frames and then you put the brace frame. Now you look how much force is going to be going to each moment frame and how much force is going to be going to each brace frame. So let's draw here the force for you. This is not the reaction, this is going to be the action, right? So usually you draw this, you say here's the force, another force goes here, another force that goes here, another force that goes here. You can have here 4 forces, right? To this moment frame. Total forces here, when you add all of these forces to each other, it's going to get you V. So this one, I'm going to call it here F1 because it goes to moment frame 1. This one, I'm going to call it F2 because it goes to brace frame 1. This one, you can call it F, let's say, brace frame. So I'm going to say BF2. Let me call this F BF1 is the force that goes to brace frame 1. This one I'm going to call it force moment frame 1. Give it the last force here. You just add all of these forces, you're going to get V, which is 100%. Now, if you do the analysis, most likely this brace frame is going to be taking the same amount of force as brace frame number 2. These 2 forces are going to be the same. And also, most likely, this moment frame is going to be taking the same force as this moment frame. Very close to it. So I'm going to say they're going to be the same. Now, let's add the moment frame forces together. So I'm going to call here the moment force. The force that goes to moment frame. Let's say the force to moment frame equals, it's going to be called force MF1 plus force MF2, if this makes sense. And the force that goes to the brace frame, I'm going to call it force to brace frame, equals force brace frame 1 plus force brace frame 2. Which means add both of these two forces together and add both of these two forces together. Now, if you add this force at the mount frames to add it as a force at the brace frames, it's going to be equal to V. So you can also conclude this. You can say V equals force to the mount frames plus force at the brace frame. How about percentage-wise? What is the percentage of the force of the mount frame divided by V? So I'm going to say here, force of the mount frame divided by V. I'm expecting it to be 10%. So I'm going to say maybe 0.1. How about the rest of the force, which means force to the brace frame? Force of the brace frame, right, divided by V is going to be equal to how much? 90%. We put it here. Which means this moment frame doesn't really take much force. All the force can get sucked by these two moment frames because they're very stiff, they're strong, they're going to be taking most of the force. So we need to do something about this. Otherwise, this moment frame, if you take this force here, design the moment frame for it, you're going to end up with a very small moment frame in terms of the section, the size of the members. So we don't want this to happen because we know that this is going to be stiff anyways. Are you guys okay? Are you following me?
Yes, Professor.
Okay, very good. So what the code says, now remember this discussion here, and let's move it there. So I'm going to make a copy of this and go there. In D1, which I like to use, it says the moment frames, your moment frames, should be capable of resisting at least 25% of the seismic force. What is the seismic force in here in my equation? When you say here seismic force, what is the seismic force? Prescribed seismic force is GBV, correct? And the force that goes to the moment frame, what is the force that goes to the moment frame? Let's see, force that goes to the moment frame or capable of resisting, I guess you're talking about this force here that we're just talking about, which is the force in the moment frame. What do you say if you take this force here? This is going to be the design force now. If you take it, you divide it by the V, the total base shear, they are looking for at least 0.25. At least, so I'm going to say at least, right? It's going to be at least to resist this force here. Meaning your analysis here, based on the stiffness, is going to be yielding a force on the moment frame which is nearly 10%. You cannot really use it in your moment frame design. So what you need to do is to take it, amplify it to make it at least 25% of V. So how do you do this? So after you do this analysis, right? You come back and say, no, I'm not going to be using this force. I'm going to say the force in the moment frame that I'm going to be using in my design is going to be equal to at least 25% times V. So I'm not going to be using this. I don't like this value. This is true. This is based on analysis, right? But the one finally that I need to use it in my analysis is going to be equal to 25% of the prescribed seismic force, which means the base shear, the total base shear. Is it good? How about the force that go to the brace frame? Should I make it 75% or should I make it 90%? You say, you know what? No. The force that goes to the brace frame, I'm going to keep it to be 90% of V. So as someone here is going to ask me a question and say, where did you get this 10% or 90%? Is this in the code? I'm going to say, no, this is going to be based on your analysis. I'm just throwing a number here, which means someone else is going to come up maybe 12% and 88, maybe 9% and 91. I have no idea. It's just a number for sake of discussion. And this number here is going to be based on analysis, means on this, is going to be based on the stiffness of the structure system that you put in there. You put a small moment frame, when it comes to the size, it's going to be sucking less load. You put a stronger one, it's going to be taking more load. So the final force that you need to design your moment frame for is going to be at least 25% with the base shear. But the brace frame is going to be designed for whatever force that your stiffness distribution is going to give to you. So this doesn't mean that you're going to be designed this here for 75% for the balance. No, it means that you're going to keep this to be 90% as is. You don't change it.
Professor?
Yeah.
You said that the V shear force is equal to FMF plus FBF, right? But the
FBF is the
25
force that goes to the brace frame, and this is going to be the force to the moon frame, the design
Yes,
one.
sir. But sir, if we add both of them, like if a moment frame is 25% of shear force and brace frame is 90% of shear force, it will be
Yeah.
more than 100%.
Yeah,
So wouldn't
this is
it
what the
be
code
more
says.
than V?
Yeah, this is
Our
what the
shear
code says.
force?
Yeah, they just want to be sure that you don't use a very tiny steel moon frame when it comes to the size of the members, and you just say, okay, this is what the numbers are giving me. So they want you to have a moon frame that's going to be at least taken 25% of the base shear.
So basically, it's more for safety factor. Our force is more than shear
it
force
is not a
for
safety factor. It is confirmation of the code. It's the limit in the code when it comes to moon frame design that your moon frame needs to be a little bit larger. Yes, but I wouldn't call it safety factor. I'm going to say this is an emphasis or confirmation that your moon frame is going to be good enough to be able to act in a ductile manner.
Okay.
Because once you use the term safety factor, it reminds you, yeah, it's kind of safety. It's more safety, but not a factor. Yes, it's more safety for safety of the building and for better performance, higher performance. Right, let's just take the term factor out. Otherwise, someone's gonna say, "Is this ASD design?" This is where you have the safety factor.
Professor?
Yes.
If the distribution of the forces that you determine, usually we have like the story shear acting in the center of the mass of the building, but it's not coincides with the center of gravity because of the live load existence and geometric nonlinearity. So do we need to consider torsional rigidity, torsional stiffness when we dividing the forces to the moment frame and the brace frame?
This is gonna be beside all of this discussion. At the end, we're gonna have this eccentricity, and we have eccentricity and applied force, and we have eccentricity due to natural causes, because the location of the center of gravity might not be in the center of rigidity. And then also you have this accidental eccentricity, right? Which is 5% of the total length, which is not covered here in this discussion. But thank you very much for raising this issue here. All right, are we good?
All right, thank you.
Yes.
Okay. Thank you. All right, good. So actually, I could maybe bring you a building like this and give you some numerical values for the forces. I'm gonna say I was doing a design, and the forces I obtained here, let's say that was equal to 100 kips. Just throwing a number there for our sake of discussion here. I'm gonna say it's gonna be 100 kips. The force here, maybe 5 kips, right? Is gonna be 45, 5 kips. Say 100 is divided into 5 and 45, 45, and then again 5, total of 100. I'm gonna ask you, what is the design force for this moment frame? I'm gonna do it here quick, and please, I want you to follow me because this is gonna be in your midterm. Are you guys awake? Yes?
Yes.
Yes, we're
Yes.
Yeah,
here.
we said midterm. Yes, of course, I need to be awake if you said midterm. Yeah, why not? Yes, this here is gonna be equal to 100 kips. Of course, I'm gonna be changing the numbers. It doesn't need to be exactly 100 kips, right? 100 kips here for the total base shear. This FM1, I'm gonna put it equals 5 kips. If B1 equals, I'm gonna put here 45 kips. If B2 is how much, did we say?
45.
45.
45 kips. If M2 equals?
5.
5 kips. Great, total of 100, so it makes sense. Now, what is the design force for this one moment frame only? I'm going to say design force for one moment frame only, not all moment frames. I need to put it right here. I'm going to say design force for MF1, moment frame 1. Right? Now, how this is going to get done? Okay, I need to think about this. I'm going to say, based on this force analysis, the force at MF1 based on stiffness analysis and system distribution says here 5 kips. But the code says use 25% minimum. For what? Minimum of what? So I'm going to say here 25% of V. How much is 25% of V?
25 kips.
25 kips. Does it mean that I need to design this moment frame here for 25 kips? I say no. Let me go back again to the table. Try to understand it more so that I don't do this mistake. It says here, dual system with a special moment frames capable of resisting 25%. So let me look here at the moment frames. How many moment frames do you have? 2. Each one supports 5 kips. So the minimum force that both of these 2 moment frames is going to be supporting is going to be how much? 25. Currently they support 10 kips. So each moment frame is going to be how much? This is going to be 25% of V, right? So I'm going to say Fm, the force in moment frame 1 for the design is going to be equal to, I'm going to say here 12.5 kips. This makes sense, guys?
Do you mind repeating it one more time, Professor?
Yeah, absolutely. So what we have said here, each one of these moment frames would resist 5 kips, but we want both of them to resist at least 25% of the phase shear. So this 25% for the phase shear is going to say for all moment frames, not just for one moment frame. Since both moment frames supporting the same amount of force, right, by stiffness, let me take here this 25 kips and distribute it between these 2 moment frames. So you have here a total of 25 kips and you have 2 moment frames. How much would you give each one of them? I'm going to give this guy here 12 and a half, 12 and a half.
Yes, that makes sense.
Okay, good. All right. So we're done with this example?
The capacity of moment frame 1 and 2 is 12.5 kips, right?
Yeah, not the capacity.
And
This is going to be
they
the
are
design force.
supporting.
The design force. And by the way, this is not negative. This is just a small dash, right? So let me
Yes,
just take it out. I don't want someone to come here and say FMF1 negative design equals no. Okay.
So their capacity is 12.5 kips, or is their
This is
demand
going to be the
12.5?
design. This is going to be the demand on it. This is going to be the demand force that you need to design for. The capacity could be higher.
Okay.
All right.
Okay.
All right. So we're done with this example. It's clear. So okay.
Yes,
Let me do another example, very similar to this. I'm gonna put here the 100 kips, and this one here, I'm gonna put here 15. And here, how much should I put here? If I said this is gonna be 15. 35. 35. It's gonna be 15. How much is the design force for each moment frame?
15.
15 or 12 and a half?
15.
15?
Yes.
Michael, I add? 15 or 12 and a half?
For FB2 or FM2?
No, for this guy here. How much is the design force for this moment frame?
We agreed on 12.5 because it's taking the same force as FM2.
Yeah, and then I said we are done with this example, right? Now this is a new example. In this new example, I redistributed the force differently. I said that this guy is going to be taking 15 kips based on stiffness analysis. This guy taking 35, 35, 15.
Yes.
So now, finally, how much should I design this for? Should I design it for 12.5 or should I design it for 15?
It should be designed for, well, if we take 25% of V,
I
that's
take 25% of the total force turns to be 25 kips for both moment frames. Now I'm wondering, what is the design force for MF1?
it should be 15 because the 25% is minimum. And if we,
Exactly. Yeah, okay. Distribution says here 25, 15 kips per each, right? And I have this condition, according to the code, when you have a dual system, that I'm gonna have at least 25% of it. So I said, okay, this is at least, but stiffness distribution here, it gave me higher forces than the 25%. So actually I should be using this force here. Okay, you're good?
yes, I'm good with that.
Right, all right, great. So
Professor,
that, yes,
do force in moment frame 1 and moment frame 2, do they always have to be equal or can they be different? For example,
they
force
can be
in
different.
moment frame 1.
They can be different. They can be different.
Okay.
They can be different, but distributions can be relative to each other. For example, if this guy here takes 10 and this guy here takes 5, right? So you have total of 15. Now you'd like to bump it to 25. So when you bump it to 25, right? You're going to say currently the support, let's say 15. You'd like to bring him to 25, and then you find out the ratio of this number here. You're going to say, well, you're going to find the ratio of, you're going to say 25 plus 25 divided by 15. It's going to be your amplification factor. Does it make sense?
No.
No? Okay.
Can you repeat?
Yeah, sure. Let me put here the analysis, right? So I'm going to say here, F in moment frame 1. So I'm going to say the force in moment frame 1 is how much? We said it's going to be 5 kips, right? And
Yes.
moment frame 2 is going to be 5 kips. And then I have also brace frame, right? So I'm going to say the force and the brace frame 1 and the force in brace frame 2, correct? So I put here 45, 45, total of, so let me put here the total, all of these forces, right? 100. All right, so this is going to be based on the stiffness distribution. For the moment frames, I'd like to see at least 25%. So I'm going to say at least, in this case, force in the moment frame is going to be at least 0.25, right? 0.25 multiplied by 100. This is going to be minimum, right? This is what I'd like to see. It means both of these two, I need to bring them up to 25 kips. So I'm going to say kips. Let's say here minimum. How about that? Right? So how can I do this? I need to find here a multiplier, right? And these two numbers can be different. So for example, if I have here 5, maybe I have here 10, and it's going to be 40, right? Maybe this is going to be distribution to end up with a total force of 100. How can I do my equation here to solve this issue? I'm going to say this is going to be the minimum force, right, in the moment frames. But the force in the moment frame, based on this distribution, is going to be equal to this. Is going to be equal to this plus this. It's going to be equal to 15. The increase factor, I'm going to say here my factor. I'm going to say the factor. Increase factor is going to be equal to the 15 and the 25 divided by 15. So I need to increase this by this factor, right? Does it make sense?
Yes,
Both of these two, they need to be increased by this amount. So how can I do this?
Okay.
I'm going to say, let me take this force multiplied by this factor, right? Same thing here multiplied by this factor. So my design force now becomes how much? For this moment frame, it's gonna be 16, and this one's gonna be 8 because I have this multiplier.
Okay.
Let's say a different distribution. I have here 5 and 45. Look what happened. Exactly 12.5, right? So it is
Yes.
doing it. I have this is, let's say, to be 6, and this is gonna be 44. Here's gonna be the design force on this system.
Okay.
It's gonna be minimum design force, right?
Yes, sir.
So if you like, let's say that you're doing this for your project, you can come here and say, well, I'm gonna be taking the maximum of both of these two values, right? Does it make sense what I'm trying to do? The maximum of these two values. Just in case, if you have here 15, then you have here how much? 35, 44, and 6. You see now what is going to be designed for? This is going to be based on the distribution, right? This is to make it 25 kips. Look at this. Both of these two is going to be 25. If you add all of this, right? It's going to be 25 kips. And this is the one that you're talking about. You say it's going to be, look at this. Okay, let me take this out for now. Because the one that you're discussing here, what's going to happen to the design force for this brace frame? You're going to say design force is going to be equal to this guy, right? So let's say here also I have 15, and this is going to be 35. Look at the final design forces, 15, 35, 35, 15, right? But if I put this here to be what? I'm going to put this here to be 5, and then you have 45, 45, and 5. Look how much design total forces I'm going to be designing for. It's going to be 115. This is exactly what you indicated last discussion, right?
Yes, sir.
Right? Any questions on this? It can be in your exam, and this kind of conceptual. This is not really analytical. This is just based on understanding, and the numbers are very simple. So I'm not doing here any design work. Good thing is recorded. All right. In the following slide set, it shows you here how to do the risk category. And once you have the risk category, you're going to be doing the size design category. This table is not really in the code. I just made up this table. This is going to be the table that you see here in the code. To find out the design risk category, you need to know the occupancy, and your occupancy category is going to be like this, 1 or 2. It's going to be yours. You look at the SDS, and also you look at the SD1, right? So find out where you stand in terms of the SD1, and let's say that you're going to be here, right? SD1 here is, let's say, I'm going to put it here to be, let's say, 0.15 G. So you're going to be at risk size design category of C. And then also do it for the SDS. And for the SDS, find out your SDS is equal to 0.6. So you're going to be here. So based on the SDS, your risk category that you have, your size design category is going to be D for the SDS. For the SD1, it says here is going to be C. Which one to pick? You can say, of course, you pick the C one, the one with the highest designation. So if you have C or D, right? Of course, you're going to pick D, the highest. And in also in the code, they have a discussion when S1 is greater or equal to 0.75 G, and then it says based on this category, they can give you here size design category. So actually in this case, I just put in the table format to be very similar to this. It's gonna be simple for you. You look, if your S1 is gonna be equal or more than 0.75 G, you just use this table and forget about these two tables. So if this is gonna be 0.75 G and you have an office building, you just say my size design category is gonna be E. That's it, you're done. You don't need to continue. But if it's gonna be less than 0.75 G, you need to go through these two tables and you find out the designation for the size design category, and then you pick the highest of the two. So for example, D is gonna be higher than C, higher than B, higher than A. This is the way it works. I have an example, and I want you please to read these examples. They should help you out if you don't have any other source, or if you haven't done the seismic analysis before, according to the CBC building. They give you here the SDS and SD1 and S1. Say determine the risk category and importance factor. I have elementary school and I have more than 3 people. So in this case, I'm gonna have importance factor. This is gonna be seismic risk category, or the risk category is gonna be 3, and your I sub E is gonna be 1.25. We covered this last time. And once you have this S1 of 0.75, 0.75 and more in risk category 3, I'm gonna go back here to look at it. This is gonna be E, because S1 here is gonna be equal to 0.75 G, and the risk category is 3, so my site design category is gonna be E. That's exactly what I have there. Factory produces hazardous material, and this is gonna be risk category is gonna be 3. May affect the public, and this is gonna be will be constructed at this latitude and longitude. So actually, in a case like this, you're gonna be doing whatever that you need to do for your project. You need to go to the website, and there is one for SIAC, and then also another one for the ashpod, and then based on this, you can find out the SD1 and SDS and the whole thing. The risk category is gonna be 3. Importance factor is gonna be 1.25. Seismic design category SDS is gonna be based on SD1 and SDS after you determine these. So I understand that some of you guys, you have done this already, you have taken it, but I just showed you here this as a kind of refresher for people who may forget it. But if you have any sources or if you know how to do it, you don't really have to go through this. But it tells you here, how do you take it from the SS and S1 that you find them in the map and then determine here SDS and SD1. And I have it there. Now, based on these 2 tables here, if you do the first table, based on the SD1, you get size design category B. If you do the second table, you are going to be getting size design category C. This is a discussion I was talking about here between these 2 tables. So let's do this in detail, just this element here. My SDS equals 0.289. Okay, so remember this. The SDS 0.289. So let me go to the SDS table. 0.289. Where do I fall? 289. I'm here, right? Between 167 and between 0.33. And the risk category is gonna be 3. So I'm at B. So size design category B. Let me see if this is correct or not. They say yes, B. Based on the second table from the SD1, SD1 says how much is SD1? 0.167. Okay, I'm gonna go back here. Yeah, we're looking at the SD1. 0.167. Is this on? 167 is gonna be here. And risk category is gonna be 3. So my size design category is gonna be C. So one of them says B, the other one says C. Now which one to pick or which one controls is gonna be C. Okay, good.
You wouldn't choose the higher risk category?
I did. You have B and C. C is higher than B. So
Oh,
the
okay.
highest is gonna be E. So A is gonna be the lowest. So it goes from A is lowest and then B, C, D, E. And then also you have F, like in here. So F, this is gonna be the worst case for the higher in seismicity.
Okay, just because with the other one, I think we chose C rather than D on the other one, but
Oh, the other one, which one?
you were
here?
just showing, yeah, you're just showing the example of like C or D, and we chose C in the end. So I thought,
No, I guess I chosen D if I'm just did a mistake.
oh, okay,
I didn't
Okay.
mean that. You just take the worst case, the one that controlled.
okay. So worst case
All right.
is the higher letters.
Yes. Yeah. So what is the importance of this size design category? Let me ask you here. Anyone remembers? Why the size design category is important?
Because
the
we have to
selection of
design according to that.
for the selection of building system.
Yeah, and what
then
else?
Selection of ductility or factor.
It's regarding the occupancy.
Okay, let me open this.
The type of building that you're going to be constructing, so for safety.
Yeah, and look at this. Here's the importance. Just to remind you, because this is also giving your midterm, right? Based on the seismic design category, you can figure out one of the things, right? Is going to get affected greatly by this. Based on the seismic design category and the structure system, we can figure out the height of the building. So the selection of the structure system is going to be really based on the seismic design category. So, for example, if I tell you here, I have a building that I'd like to put in seismic design category D. So I pick this seismic design category, right? So you cannot change this. This is going to be based on the site, correct? Not on the system. And my building height is going to be 200 feet. Can I use anything here in this page? Any of these systems?
No.
Anything here?
No.
No,
No.
not permitted under 60. I have 200. How about here? Cannot do it.
No.
Oh, no limit. Amazing. This is good, right? So I can use this because it says here's no limit. But if I told you here, for example, 150 feet, maybe you can come here and say, you know what? You can do this or this. Pick one of the two, right? So I have here more options. Or you can have this. Anything that says here no limit is good. Not permitted or gives you a limit, and this limit is lower than the proposed height of your building, it means you cannot really use it, right? So what's going to happen also in your midterm, I'm going to give you a seismic design category and ask you some questions. So be familiar with this, with these tables. This is table here 12:1. This is going to be famous table that we use. I don't know where it says 12:1. It's not written there, but it's called here table 12:1, like this. Twelve to 1. It's like this. Very famous table in the SE. So be sure that you understand all of these factors. This R factor, what does it mean? And this D, if you have this D, this height, no limit, not permitted, right? Or I may ask you a question. I'm going to say the building height, the proposed building height is this much feet, right? I'm going to say site design category is going to be this much. Which of the following buildings that you're going to be able to build it according to the information provided above? And I'm going to say A, for example, the answer A is special reinforced concrete shear walls. And then you look at this, you check this out. And then another one, I'm going to say building frame system. I'm going to pick here B1, for example, steel eccentric brace frame. It says here 160. The other one, maybe a mount frame. The last one, maybe a mount frame. And of course, it's going to be your selection is going to be whatever applies, right? So maybe you have 2, 3 options, maybe all of them, maybe none of them, right? It's good to be built at this location. All right, questions before I leave and let you go? If any of you didn't finish yet your oral or your discussion for your midterm, please stay, hang around, or see me in the office hour after a couple of minutes. All right, you guys have a good night. I'm gonna put on.
Thank you, Professor.
No problem. I'm gonna put on the meeting for the office hour right now in a second.